Welcome everyone to our lesson on intercepts and symmetry types. The first type of intercept I'd like to describe is the x-intercept. X-intercepts are places where your graph will cross the x-axis. Some graphs have multiple x-intercepts, but the idea is that the x-coordinate is a number on the real number line and the y-coordinate is 0. So the way you find an x-intercept is to let y equal 0 and then solve for x. Likewise, a y-intercept is a place where your graph will cross the y-axis, so the x-coordinate is 0. So to find a y-intercept, you'll take the equation for the curve, let x equal 0, and then solve for y. Now some graphs have no intercepts at all. Others have multiple of each kind. Some only have one of each kind. So you'll have a variety of things that you encounter. I'd also like to speak to you about symmetry types. Okay, the first type of symmetry I'd like to discuss with you is x-axis symmetry. And you have x-axis symmetry when every ordered pair on the curve that you have has a mirror image of itself about the x-axis represented on the curve. That would mean that all of the x-coordinates are the same, but the y-coordinates are opposite. And that also gives you an idea of how to handle a symmetry test. Because if your y-coordinates are opposites, and you substitute those into your equation, and you get the same result, then you know you have x-axis symmetry. Likewise, y-axis symmetry, if you have an ordered pair on the graph, if you have the mirror image about the y-axis, then your x-coordinates are going to be the opposite of what they were, and the y-coordinates will be the same. And again, this is how you would apply the symmetry test. If you had an equation and you needed to take an equation and test for y-axis symmetry, you would let the y's stay as they are in the equation, and then you would replace every x with negative x, substitute in, and see if the equation cleans up to be the original. All symmetry tests work in this same type of manner. Origin symmetry. If I have a point on the curve, I measure the distance, straight line distance to the origin, project across, then I should find an ordered pair that has an opposite x as well as an opposite y coordinate, and that's origin symmetry. Okay? Now in just a moment we'll look at some examples. So let's just get this written down here. Okay, here's an example. In your catalog of functions, you will recognize y equals x squared plus 5 as to be related to a parabola, either opening upward or downward. You can do some reasoning and plotting points, certainly, to pick the graph, and we'll do some of that here. But the question ultimately asked you to find the intercepts and test for symmetry. And if an answer does not exist, enter D and E for does not exist. If I wish to find an x-intercept, I'm going to let y equal 0 in the equation, and I'm going to solve for x. And when I do, I see that I get the result x squared equals negative 5, which is not possible. So this graph has no x-intercepts, which means that we rule out this guy as well as this guy as far as options for our graph. Your y-intercept, you're going to let x equal 0, solve for y. In this case, we see that we have a y-intercept of positive 5. Now the question does indicate an ordered pair. Parentheses are already included for us. So our first coordinate is 0, our second coordinate is 5, which tells me that this guy is not the graph, leaving me this choice. Now, I can also verify if I put in 1, I get 6, and -1, I get 6, and so forth. You could test some more points. Now, what about the symmetry? Well, looking at the graph, we can see that the graph is a nice symmetry about the y-axis case. Some graphs have multiple symmetry types. This one does not, but be open because there could be more than one correct answer and you'd need to choose all the correct answers that apply to your graph. Okay, lastly, let's just take a quick visual look at symmetry. Your first graph here has no symmetry. I don't see a perfect reflection about the x-axis because I see that this and this are really not the same shape. It doesn't reflect about the y-axis nor the origin. The second graph does not have y-axis symmetry nor x-axis symmetry, but it does, as you can see here, have symmetry about the origin. And your last graph if we look at all of these potential ordered pairs, has nice y-axis symmetry. Okay, so it is possible not to have any symmetry type apply or to have multiple types apply.